What we mean by planar transformations, we start in a particular coordinate system, maybe the u, v coordinate system. And then we have a set of functions that take in the uv coordinates, plug it in, and they say how those uv coordinates are now going to be mapped into the x coordinate, y coordinate system between two different functions. And so you take your set inside the uv space and see where it gets mapped into the XY space using these function notations. We usually want the typical things. We want these functions to be continuous, and we'll need them to be partially differentiable uh, on its domain in order for it to be nice enough for us to use. I've tried to make an example here in GeoGebra. You can see this is the UV coordinate system. Now, I want to be able to graph both images. Sorry, I want to be able to graph the original set and its transform set on the same graph so you can see both of them simultaneously. You should remember this purple G region really does belong on the UV coordinate system that you see here. We find the XY coordinate system, which I'll use the same grid simultaneously to represent the picture, by plugging any point inside this UV region. So in this case, 2 for the, I guess, U and 3 for the V, into this set of equations defined above. So I'd substitute a 2 in for here. That would give us a 4 times 1/2, which is going to be 2 plus, looks like 3 for the v, which would be, so 2 plus 3 is 5, so the y coordinate would be 5. I would find 5 over here on the what I want to be my y coordinate eventually. And then my x coordinate would be, again, I plug in a 2 times a negative 1/2, that's a negative 1, minus, oh, sorry, that's a v, isn't it? Oh, and then I'm plugging in a 3, actually, which would be a negative 1.5 minus a 2, so negative 3.5. So this point over here will get mapped to x coordinate negative 3.5, y coordinate 5. If I want to see the transformation of the whole set, I click on this button, and you can see that, oh yeah, it looks like it did get mapped over there. As I move the point around, it's automatically remapping every point in the UV coordinate system to the corresponding point in the XY coordinate system. Once again, I've superimposed the XY and the UV scales onto the same scale, so you can see both graphs at the same time in the same picture. So we want our transformations to have some nice characteristics. Like I said, we basically want them to be smooth or differentiable, but also there's an additional characteristics. We want to make sure they are one-to-one transformations. What that actually means is that if you have two outputs that equal the same, that must imply that they came from the same input. In terms of this picture, the only way I can get, say, this point of x and y over here, this coordinate point, can only come from one point inside the domain of G, which happens to be this UV, if it is in fact a one-to-one transformation. If it's not one-to-one transformation, I can find some point inside this R region, maybe this point over here, which I'll try to get to. Okay. I should be able to find some point in this region that comes from multiple UVs inside the G. In this particular map, that's not the case. This is a one-to-one map. I'll try to come up with another example for you where you can see where it's not one-to-one. This is an example of a different transformation. You can see how I changed it. I used a simpler one for me to show you that this one is not one-to-one. Notice I have this point in my domain. I plug it into my transformation, it gives me this point in the range, in the XY plane. If I go down here to the mirror image on the of the relative to the U axis, I end up getting this point over here of UV getting mapped to exactly the same point over here in the XY. So this XY point inside the image, my transformation, can be, the transformation has two different points in the domain that sends it out into the range. So it's not one-to-one.